So our first presentation of the day is by Nelson Pass, who I think you all know.
Yeah, there we go.
Yeah, this show just wouldn't be what it is without Nelson having helped us out, and that's happened a lot of times in a lot of areas. Your talk today is about amplifier design in the neo-postmodern era. I added neo to that, incidentally. That's obscure enough that it could be anything, and that's what it's going to be, anything, right? Okay, so God willing, with the projector, I present Nelson Pass.
Oh, good. That's excellent.
Your box then. We need some mics.
Okay, well, once again, as always, what we do here is I strung a bunch of pictures together, and then I talk about each one. And the essence of this talk is on the first watt F6 design, which those of you who hang out in the forums at DIY Audio know that everybody has.
Make it a little bit better. Two microphones. Oops. Wow.
Too much feedback.
Use the better.
Well, I don't know what we can do with this here. I can lower this down a little bit. Yeah, that'll be all right. Okay.
Wow. Anyway, let's vote here.
All right. Oh, very good. Okay. That's not me. I have two cell phones today. The F6 is, I looked around for something to do, and I saw that the last project was F5. Here's the F6. But I did want to do something, as always, a little different. And what drives this are a couple of things. One is that I really like to use up these nice powered JFETs, the ones that are no longer being made as of last week. The bad news being that SemiSouth apparently has closed its doors, and the only thing I can say is that I bought a big pile of them, and so I have every intention of just marching ahead. But I announced this, and I did so with a nice little teaser schematic of what I had in mind. Would you like to kick the next slide? Yeah, there you go. And I published, I published an erroneous version of this schematic. And what I'm looking at here is a push-pull Class A powered JFET amplifier. And the parts that I can get of this variety are only available as N-channel versions. So you don't have complementary parts. You don't have P's and N's that can operate at the opposite polarities of each other. So usually some special accommodation has to be made. In a lot of amplifiers, you see what's known as quasi-complementary, stuff that dates back to RCA and the old Harmonic cardons and stuff. And stage linear, things that came out of the late 60s. And they inevitably involved some additional circuitry that allows this device down here, which is an N-channel part, to behave as if it were a P-channel part. There's some flaws with that, not the least being that there's really nobody making true complements of P's and N's. They aren't truly symmetric. That hasn't stopped anybody. It certainly hasn't stopped me. But I saw an opportunity here maybe to play around a little bit. And I had screwed around a little bit with a transformer recently in a project that was referred to as the M2, where I use the M2, or I use a power transformer for the entire voltage gain of the amp. You drive the primary of the transformer, and the secondaries have more windings on it, and so all of your voltage gain is derived to that. And then a complementary output stage simply followed that, and voila, you've got a single stage amplifier with, in this case, no feedback. Nice little amplifier. and I am still selling those just in case you have a need. This one, I want to do something a little different, and I still had a stock of transformers that I'd been playing with. And I decided that first off, I wanted to build an amplifier which was push-pull complementary, but had really good, decent symmetry between the plus and the minus stages. And one way to achieve that, the kind of way that they used to back in the 60s, before they had, shall we say, more advanced techniques, is they used transformers. And like I said, I had some laying around. In this particular case, it's the Jensen transformer, which has 4 windings, which are all identical. And I have, I think there was an F0, a V0 also. Yeah, can we go back one? Yeah, this is it. Okay. This is the basic circuit here. You've got a primary winding. It drives, it's just a 1-to-1 ratio. It drives a power transistor on the top end, and it drives the negative transistor out of phase. These two systems are actually driving them out of phase. And you get a nice push-pull circuit, and you're using only N-channel devices, and it has really good symmetry because these circuits are identical to each other. They might look a little different, but this one's being simply isolated out of phase. And you can build this amplifier, and it actually works quite well, all by itself, almost as presented. However, finding this particular type of transformer is kind of a rarity, and so you go through the catalog, and most of what you find are 2 primaries and 2 secondaries. And so in the next, and one other thing. These are bias voltages. The FETs in these cases have to be given a positive gate voltage relative to their source pins. These are the sources, that's the gate, those are the drains, and you've got to put a little positive voltage on these things to get them to turn on. In this case, something on the order of about 1.2 volts will get them running. So you have to provide that 1.2 volts. So in this circuit, I've specified that it has a voltage source, and in each case, the voltage source is simply relative to the output of the device on its source, and it's relative down here. And you bias it up with about 1.2 volts, and you have actual amplifier. You could almost build it exactly as read. There's a couple of small disadvantages with this approach, and that is things would have to be absolutely perfectly matched between the positive and the negative devices and all the other conditions, because there's nothing in here that would control the offset voltage. It might be free to drift around a little bit. So if I could have the next. So that's version 0, the most simplified. Here is what I'd call the simplified. Only it shows a real part. This is a Jensen JT123 FLPCH. It's just a nice little $30 transformer that mounts on the circuit board, and I have paralleled the 2 primaries. In case you don't know, the thing about the transformers is these little circles indicate polarity of the windings. So for instance, if I put a positive voltage on this, a positive voltage will appear there, a positive voltage will appear there, and a positive voltage will appear there. And these 2 I'm just running in parallel, but in these 2 you see that in fact the positives, they've been flipped so that it's inverted. When a positive signal goes into the input, a positive appears there and a negative appears there. And in a circuit like this, what you've got is a positive will appear at the output because this will follow that, and this transistor will begin shutting off, and it'll support the idea that that one is going positive. And that's the whole basis of a push-pull circuit. There is a couple other differences. The primary one, though, that is of interest here is you'll see that there's a little more detail on the circuits that are driving these. Specifically, the most interesting part is this, which is instead of referencing this back to the source as I did in the previous circuit, I referenced it to ground. And this solves the offset problem that I was talking about. The transistors don't have to be perfectly matched, and you don't have to tweak them and make sure that the temperature is always at the exact same spot, and so on. Because as this output starts to drift, this will start driving that transistor in such a way as to compensate for that. So in fact, at this point, what we've got is a circuit where this voltage here determines the bias of the amplifier, and this one determines the offset voltage of the amplifier. And they are independently adjustable. And in fact, a little bit later, you'll see where we put potentiometers to acquire that. This is a real circuit. You can build this circuit. For voltage, you can use anything you want. You can use a battery. In fact, a battery would be almost perfect. It's got just about the right voltage for it, a little D cell or AA cell. Can I have the next one? I did build exactly this circuit, and its distortion curve looked like this. Now, this is a no feedback circuit. Here we are down at 1/10 of a watt, and it's got 1/10 of a percent. It's got mostly a second harmonic characteristic because the two transistors are not perfectly matched. And as you can see, by the time you get to 10 watts, you're running a little over 1%. For a no feedback circuit, that's fairly respectable if you can consider it in the context of, say, somebody who might be looking at an SET amplifier that's single-ended triode or similar. But this is what it is, open loop, without any distortion. I might also add that the output impedance of this circuit is high. It's a right now, it's a current source amplifier, and it has a damping factor that's a very, very small fraction below 1. On the other hand, it works just fine. You can listen to it, blood won't come out of your ears, but it's a little high on the distortion, the damping factor is very low. There are some speakers that probably would appreciate this, and a small quantity of audiophiles who would think that it sounded quite good. Can I have the next one? Here is that same circuit. All this is still the same, but I've done something new. I put a feedback loop in it. In fact, what I'm doing is I'm using the primary of the transformer as the feedback element. When this goes positive here, if I put a positive signal here, this system drives that transistor so that it makes positive. It drives this signal oppositely, so it also drives everything positive. And the output signal, which is quite large, comes back through the feedback loop, this resistive divider, and ends up being an impedance at the other side of the primary transformer. And what it does is, first off, it's feedback, so it reduces the amount of gain. It provides a damping factor for the amplifier. It also dramatically raises the input impedance as seen by the amplifier. Without a feedback loop, the input impedance is, I don't know, last time I looked at it was like maybe 5K or so. Not awful, but not particularly high. So we've kind of morphed from a more simplified transformer with no feedback and things which are not very stable with regards to offset and so on, to something where we have DC control. We'll set this up a little bit later so that we can adjust the offset, we can adjust the current, and we can set the gain with feedback, which can lower the distortion quite a bit. The open loop figures that I was getting on the previous slide, which had no feedback in it, in other words, you just drive an input and you look at the output, had about 38 dB of gain, the open loop. And an open loop frequency response that was about 5K ohm or so, and then it started falling off. If I can see the next slide. Now, mind you, if you follow the thread on DIY audio, because far in advance of me releasing, or even for that matter, finishing this design, I had people speculating on all the things that they were going to do and how I might be doing it and so on and so forth. And at one point, you will discover that they got extremely close. And in fact, at the end, I even have a version that gives a nod to what they were doing also. In this one, we've got some fill-in here. It's the same circuit as I described before. It's still unbuffered. You're just looking at the input of the transformer. With the feedback, that input is about 20 k ohm, which sounds great, but it has a fair amount of capacitance talking to these, in particular this one coming back and talking to these through the capacitance of the windings. So it's rather limited in bandwidth, unless you have a low source impedance. If your preamp has got 100 ohms or less, it's no problem. If your preamp is 600 ohms or a K ohm, it's gonna be real soft on the top end. Nevertheless, this has an open loop. This has a feedback gain figure of let's see, what was it? I think it's about 20 dB. Yeah, it's 20 dB. And that means that it's running about, let's see, pardon?
5 times. 122.
Oh, yeah, that's right. It's 15 dB. It's actually a tiny bit more. Thank you. And that means it's running about 24 dB worth of feedback, I think I measured. That 24 dB of feedback lowers the distortion by a factor of more than 10. And in fact, when we look at the next slide, you can see that. It also gives me a damping factor, which interestingly is almost identical to the feedback factor. In other words, that 24 dB comes out to be a feedback comes out to be a figure of 16 times. And when I measure the damping factor of this into 8, it comes out, it's got a half ohm output impedance. Its damping factor is 16. So the damping factor is literally the feedback figure. A couple of things also. A little more detail on how those voltages got developed. Here's just a resistor that bleeds some current down through an LED. I use blue LEDs. They come out about 2.7 volts. I need 1.2 volts or so here. So I put a pot there. This 10K resistor is to keep this coil from being loaded by any of this. These coils are quite good. I've loaded them down to around 200 ohms before you start seeing them fall apart. So 10K, no problem. I do the same thing up here, little blue LED generating to about 2.5 volts here. I've got a pot so I can set this. Somewhere around midpoint, this comes up to about 1.2 volts. I bias it at about 1.5 amps. And there it is. It's a real amplifier. To see to it that this circuit maintains a low impedance, there's a cap as presented previously, but it's a rather large cap, 1,000 microfarads. When you turn the amp on, it takes a little while before it charges up and gets going. If I can see the next slide. This is with the feedback. And in point of fact, it's got about 24 dB less distortion. It's a factor of a little more than 10. You're sitting down here at 1 watt, 0.02%. Does a nice job getting up. It gets to, what do we got here? At 30 watts, it's about 0.4. It's maintaining a nice second harmonic all through this region. You can always tell second harmonic because it rises at a particular rate. If it is 0.01 at 0.1 watt, it will be 0.1 at 10 watts. It's a square root function of the power. Or actually, you could say it's a linear function of the voltage. If I can have the next slide. You can barely see this. I should have picked another color. But there is a little blue trace here. This is the distortion waveform as seen on a scope. The audio precision puts out a waveform, which is a sine wave you can see right here. And then it also has a distortion analyzer and will present to you for also display what the waveform of the distortion looks like. What you want is, as a rule, is not only low distortion, but you want a really nice, smooth character, and you want it to be as low as possible in harmonic content. If you look at this, you'll see it's dominantly second harmonic. It's up a little bit. Let's say there's some expansion at the top. It's down a little bit in a relative sense because there's a little bit of compression at the bottom, and that is the second harmonic. If you look at it very carefully, you can see a little tiny bit of third harmonic. And if we did a spectral analysis, that's what we'd see. Dominantly second, followed by a third harmonic. The interesting thing about that second and third harmonic item is it does correlate very nicely to what a lot of people like to listen to. Oh, thank you. The first person that I heard who actually made some commentary on that goes back to Jean Haraga in I think, Revue de Son. Wrote an article about actually amplifiers that are kind of similar to these, very simple, typically no feedback designs. His comment was, oh, I really like the amplifiers that have second harmonic in about this much, followed by a little bit of third harmonic, and then nothing else. Well, nobody's improved on that observation. That's pretty much, if you're going to have distortion, that's pretty much the most euphonic. Interestingly, he didn't want pure second harmonic. He wanted a little third mixed in there. I can tell you for a fact that most of the amplifiers that I've built that have really done well in the marketplace in terms of how people have viewed the sound started out as being very dominantly second harmonic at low power levels, and then as you climb up the wattage ladder, you find yourself with a more and more of a ratio of third harmonic, and up toward the top, they start becoming third harmonic beasts. It's odd, but we are talking about human ears, and you always have to remember that the ear is not a microphone, and the brain is not a tape recorder or particularly a spectrum analyzer. It's a very, very complex neural network that I'm sure Siegfried would be happy to tell you all about, that in many ways defies our ability to deal with it analytically. A lot of this stuff is simply the result of observation. This is what I like, this is what I perceive, and it's difficult to put an objective label on it. If I can see the next slide. Here's that same amplifier into 4 ohms. It actually does quite well. Well, the other one was making it up to 30 watts before it started clipping. This one makes it to 50 watts. Just above that, I can assure you, it just jumps right on up, so I'm not showing it to you. But it holds up very nicely. So it's a good amp for driving reasonably low impedances. This has distinguished from, yes?
Just to clarify, that's 50 watts out of one pair of SITs?
They aren't SITs, they're just JFETs.
Oh, so like R100s? R100s or R120s?
Those are R100s.
That's awesome.
Or R100As if you're shopping at Mauser. Does a good job. I didn't even bother to read it at 2 ohms, but you know, I don't expect any miracles on that front. Can I see the next one? This is distortion versus frequency. This phenomena is all transformer. That is to say, at the low end, the transformer's inductance is lowering its impedance, is becoming a little less effective as a transformer. The distortion goes up a little bit. At high frequencies, the capacitance associated with the windings that are very, very close together. This particular transformer is quad filler wound. They take 4 wires, string them together as one, and then they wind the transformer. And it gives you rather large capacitance. I speculate that, in fact, you can get more bandwidth out of other devices that are not quad filler wound. You probably will trade that off against some other parameter, but it's easy enough to try this stuff. There's no magic associated with a particular choice of parts. Can I have the next one? Frequency, this is the open and closed loop gain of that circuit. 38 dB, 39 dB of gain. Here we are at 5K, it's rolling off. Here's after the feedback loop, it's 15 dB. We have 24 dB worth of feedback. You see it here, and then you also see the roll-off finally coming in, and it makes it to 50K, and then it just floats away. And the square wave on the next slide. And then this is a 5 kilohertz square wave at 1 watt. It's not real fast, but it's nice and clean. It's not ringing or doing anything nasty. And so it's got a nice, sweet sound to it. It's not necessarily all that exceptional in that regard. Can I have the next slide? Oh, okay. So the problem that we will run into is the capacitance, the input capacitance of this system is relatively high. If you've got a low source impedance on your preamp, like I said, 100 ohms or less is just fine. Not much improvement available between that and, say, a 0 ohm in source impedance. However, there's lots of guys who aren't going to be able to drive that. particularly if you're running a passive preamp or anything else that inserts lots of impedance. Here is, and you'll be familiar with this, this has appeared in a number of things, including the M2 and other stuff. Here's a complementary pair of JFETs, N channel and P channel, being set up as followers. They self-bias, that is to say you can tie their gates together and a certain amount of current will run right through them, and you don't have to put any additional circuitry. So you just drive the input. You put a resistor to ground at the input so they won't wander around with no source. And you put a 1K resistor in source with the input because that's just smart. If you didn't do that, you inevitably would find some system or cable interaction or something that would come and create problems for you. But let's see. Actually, that's all we did on this particular circuit. Now, the circuits that I've been listening to are the previous one, unbuffered, and this one buffered. I can tell you also that this is the circuit that I have on display in my room. We'll hook it up and play it a little bit later. And the buffer didn't make any difference whatsoever in the specs, assuming that you were dealing with a low impedance on the unbuffered version. So all the curves that you saw before are the same. There are those that would correctly say, well, you can run a lot lower distortion if you put some resistance in series with the sources on these, because then they won't be running so close to their what's known as IDSS figure. And what happens there is that the gates start drawing a little bit of current on peaks. I tried it both ways. You know what? It works both ways. I didn't have any problems in any case. And so I left the resistors out. However, if you have FETs, or if you choose power supply values that are higher than this, or if you have FETs that have very high IDSS bias numbers, and that's the IDSS bias, is how many mils flow through the device when the gate and source are tied together. In other words, when the gate and source voltages are the same, which in this case they are, although there's a complementary pair. Now, these were chosen for 8 mils. And I have big bins and they're sorted, and I said, 8 mils. But you can get them as high as, say, 20. Or you might sub in some other FET that is much higher, in which case, at some point, you might be heating the FET up too much because the current is high. These things are rated at 400 milliwatts operating at room temperature being a false assumption. And with the 8 mils that I put on that against that, oh, gee, it said 200 milliwatts. They don't break. On the other hand, if you had something that had an IDSS of 15, if you had the V grades of these particular FETs, which are very prized among certain people, it probably would draw too much juice for you. Then you can insert some resistance right here and some resistance right there. The current goes down, and I've actually tested it, and the degradation associated with some degeneration in these two spots is negligible in the scheme of things. So you can just feel free to adjust for FETs like that. I know that lots of you don't have the luxury of being able to select out of bins just what you want. And on that note, too, we note that this is the Toshiba part, but the Linear Systems guys have got an absolutely perfect addition that duplicates, for all intents and purposes, what we would want to be seeing here. And once again, I am promised they're going to have that P channel out any minute. And I have tried the P channels, and they work just fine in this sort of device. So when they finally get them out, you'll be able to pop them on in. Let's see if there's anything else to know about this one. Nope. Let's move to the next one, if we may. I just finished talking about this. I got ahead of myself. Here's that degeneration I was talking about. Throw something like 10 ohms in there, takes the current on the JFETs down, does very little damage in terms of the frequency response or anything else, but it keeps them cool. And anybody who's making boards ought to just simply make an allowance for them. And you can always put a piece of wire there instead if you find that you don't need them. Can I see them? And we're at version 5. We're way beyond what I am running next door. Okay, these are just like the additional things that you can be doing. If I can have the next one. Version 6, the second harmonic version. Okay, now it just so happens that the second harmonic character of the two JFETs that we're talking about is kind of random. They're never perfectly matched, so typically you will see some measure of second harmonic in the output. Typically, that's about what you want. You know, a little bit of second harmonic, throw in a little bit of third, and be happy. In this case, you might find, though, when you build it, that you didn't get exactly what you want. Maybe the harmonic isn't in the proportion that you want. Maybe you actually want to null the harmonic out altogether and get the lowest possible distortion figure by canceling second and leaving only some third. These are all decisions that you can make, and I always encourage people to try it because you might like some of the results. There are people who really like pure third harmonic. And there are people who like pure second. As I said before, there's people who like both, and really a slight admixture of the two seems to be the most plausible way of building an amplifier like this. Especially keeping in mind that even if you design a certain amount of second harmonic into the characteristics of these output stages, it's going to degenerate, or not degenerate, it's going to converge on being a third harmonic as the power gets up toward clipping. At clipping, it's a third harmonic amplifier. Why? Because the clip, the distortion at the bottom and the top are usually just about identical. And so you look at it as totally dominant third, and it tends toward that as you get to the higher power levels. In something that's rated at maybe 25, 30 watts, above about 10 watts or so, you're going to start seeing that third come in there, and it becomes more and more dominant. However, assuming that you want, I have to add, I'm running a system, again, down the hall, where we have a scope on the amplifier, and we are running in what I call the 1 watt window. In that particular case, any trace that gets triggered and you get to see it, because it'll freeze for a moment, if it's below the top edge of the screen, or if it's above the bottom edge of the screen, because it goes up and down, it's less than a watt, and that's a peak. And even when it's doing that, the actual continuous power and most of the information is still sitting down at maybe 1/10 of that figure. So I'm running this 1 watt screen, and occasionally I have to turn it down because it's too loud. It's nice to have efficient drivers. Much of the listening that you're ever going to deal with is going to be down at 1 watt or less. I mean, it depends on the speaker, but where I come from, 1 watt is plenty. If you need to adjust the harmonic structure, if you feel the interest in checking it out and taking a listen to it, particularly at lower power levels, here's a nice place where you can do it. I've got an R13 and R14 that I've added to this. These are very low value power resistors, like 0.05 ohm, 0.1 ohm would actually be a little extreme for this. If you, let's say you leave that zero ohms for the R13, but you put 0.05 on here, you'll find yourself with a positive phase going second harmonic that you can literally measure. Or if you had a negative phase harmonic before you did that, you might use that to simply null it out so that you have none. Or if you had none to start with, you can generate a positive. Same down here. If you put a value of resistance up here and leave this one as shorted, you'll be tending toward a negative going phase second harmonic. The two sound different. And in fact, consistently people have come back and said, well, I hear this with the positive phase and I hear that with the negative phase. And a lot of it is, the most consistent sort of thing is that the positive going second harmonic has a little more projection to it. It's a little bit more in your face in terms of being intimate. The negative going has a tendency to be a little more ethereal and adds more depth to the quality of the sound. It's something that you can play with. And once we started discussing that online, I think we moved on to the next circuit, if I can see the next slide. And this one I have to give credit, I think, to Patrick. Is that it? Oh, yeah, there it is. What they did is they came up with this, variable second harmonic. Why not put a pod on it? So they've got, in this case, 1/10 of an ohm, although it could be 0.05, and a 1/10 of an ohm here, and you can adjust P3 and P4, up and down. It doesn't alter the bias currents. It doesn't do a lot, but what it does do is it allows you to trim the relative perfection of symmetry of the positive and negative sides of the circuit. You can use it to null out the second harmonic so that you have absolutely the lowest distortion figure. By the way, the numbers I showed you before were had generous amounts of second harmonic as part of that content. You trim this out, the distortion numbers drop dramatically, and if you're chasing the double O numbers, perfectly fine way to do it. You'll find if you go look at the F5 project that became quite popular, there was a version that was added rather quickly that had a potentiometer on the input stage that would allow you to do exactly the same thing. You could trim it so that the response of the positive and negative halves are identical. When you do that, the second harmonic goes away, and you have a little third harmonic left. But the second harmonic being the biggest, kind of the elephant on the dance floor for distortion in most cases, especially in Class A amplifiers, you can go from something that's 0.01 to something down to 0.01 very easily. It does take a distortion analyzer to do the work, though. In other words, you can screw around with it, but if you really want to just like nail it and be done, a distortion analyzer is going to be called for. And actually, I won't take credit for this. This was somebody online. I have done something cheekily similar to it on another circuit altogether, and it works very well. Can I see the next one? Oh, wait a minute. No, let's stay here for a moment. Can I go back? I forgot to mention one thing, though. When you add values of resistance there, you do alter other aspects of the characteristic. When you, and this is known as degeneration. When you, and degeneration in many circles is thought of, well, generally, thought of as a form of feedback. I always make a point of the distinction between using a feedback loop to do something, which, by the way, we're doing. We've got a feedback loop here. But you can degenerate circuits here, here, and here so as to lower the gain and up the measured linearity of the parts. This circuit is a Class A amplifier. It was designed to run to 30 watts or so in Class A mode. This calculation of the bias and the Class A-edness of the circuit depends quite a bit on having some degeneration, some linearizing, something which contributes resistance to the gain characteristic of this part. The JFETs have what are known as the square law characteristic. As you raise the input signal, the output signal gets increasingly larger out of proportion to the input signal, so that there's a square law characteristic. This, in a single-ended design, that it helps you see where your second harmonic totally comes from. All the tubes and FETs of all sorts are square law devices. And I won't speculate on the perfection of the adherence to the perfect square law for this sort of thing, but it is your basic nonlinear function that generates second harmonic. And so in single-ended circuits, that's what you get. In push-pulls, you're tending to cancel the second harmonic, and that's where quite a bit of that game is oriented. Notice a couple of things. Also, and just as an aside, whenever I use FETs, any FET, I stick a gate stopper on the gate. This is 47.5 ohms on each of these. You can often run these amplifiers without it. Sometimes they're just great. But if you're building 10 of them, several of them will not behave themselves. This one, in this design, amusingly, I took the gate stoppers up because, once again, I throw away every part that I possibly can, and only very grudgingly do I haul them back in after I discover that they're needed. I ran this one without gate stoppers, and it turns out that the capacitance coupling between these here and this, and they're all tied together in the windings, resulted in a parasitic, but only on turn-on. It would, just for a little bit as it was coming up, it would suddenly break into oscillation, and then as the bias came up to its full value, it would behave itself just fine. You'd never know that unless you really paid attention to this sort of stuff. But of course, if you shipped it, a very large percentage of your customers would complain. Last item on this is, again, I mentioned the degeneration on the output stage. Everybody, you can't imagine the number of emails and even phone calls that I get wanting to know at what wattage does this circuit, fill in the blank, leave Class A. Now, I take the blame for some of this. I wrote an article about it saying, I called it leaving Class A. And so it's become deeply associated with me. However, there's some interesting things about that, mostly that people let me put it another way. People have become, shall we say, a little over-concerned about where something actually leaves Class A, what the exact moment is, as if there's going to be a clunk or some other noise that accompanies it or something. In point of fact, actually, in a very highly biased circuit, these things approach their characteristics asymptotically. There is no real discontinuity to talk about. On the other hand, Class A is Class A. In a circuit like this, where you have square laws working off against each other, okay, and Jan, who publishes a nice magazine, not all that long ago had an article about a square law amplifier, and the major thrust of that design was, I can get you more Class A for less bias current. In other words, I can make a Class A somewhat more efficient just because I exploit the characteristics of the devices. Well, I've been doing that for as long as I can remember, because that's how I started. Here's the thing. You put in degeneration, however, and you will find with typical figures for degeneration that the current at which the output stage leaves Class A is generally regarded as being simply twice that of the idle current. If you idle this circuit at 1 amp, just sitting there, not doing anything, then what happens is when you go to swing current into a load, one is giving up its bias and the other is increasing, and you find that a 1 amp bias results in 2 amps of Class A operation. At and above 2 amps, one side shuts down and the other one is doing all the work. Okay, well, that's not the end of the world. But again, everybody here wants that Class A as far as they can get it, but none of them like heat. That's not really true. Anyways, oh, by the way, I labeled the parts here, see, so that you can see the gate and the drain and the source, because I know that's a source of endless confusion. If you don't put the resistors in there, if you don't degenerate the output stage, then the square law characteristic sees to it that you're going to get a wider band of Class A for a given bias. And I actually tested this amplifier just at the last minute, because I knew it was higher, but I didn't really remember what it was and what I expected. But I ran this circuit, or actually the earlier circuit, but with no degeneration, no resistances here. And I compared what I expected to see. It was biased at 1.55 amps. I expected to see it cut out at 3.1 amps if it was dominated by resistances in this region. A resistor that would dominate this pretty thoroughly would be anything from a ½ ohm up to a 1 ohm figure. Below that, you start getting some kind of admixture, and then of course when this is 0, you've got this incredibly tiny amount of resistance still sitting in this, and then it's a square law piece. With the resistance in there, it leaves Class A at 3.1 amps. I was driving a 4 ohm load, so you look at that, and what's that peak? That comes out to be, I think it comes out to be 38 watts. Anybody with a calculator is free to call me a liar, but it's something like that. However, if you have no degeneration on that and you're driving that 4 ohm load, it came out to be 4 amps. And in this particular case, 4 amps was 64 watts. In fact, I got a little more than 64 watts peak out of it. That's not a 2-to-1 ratio. I don't know, maybe that's about an 80% improvement in the size of the envelope, where at the peaks, you actually seeing the non-conductive side flatten out and being non-conductive. At lower levels, the sinusoidal wave slowly begins to warp and bend and round off in the kind of motion that you expect to see out of a lot of tube photos that you see. If you run these things without degeneration, you get that effect. You almost, not quite, almost double the Class A region. The other aspect of that, though, is you have to watch out for is a lot of parts have a thermal coefficient which is such that as they warm up, they start conducting more current. If they're bipolar devices and they warm up and they're conducting more current, then they warm up even more, and then they conduct even more, and you get thermal runaway. The R100s have their zero temperature coefficient somewhere just a little bit above 1 amp. If you bias it at 1.5 amps, and run it, let it warm up, it'll drift down the tiniest bit, not even enough to care about. That's one of the reasons that I can get away with this. There are people building amplifiers, actually most of them bipolar at the moment, who swear by the idea of not having emitter resistors. Same thing. This is a source resistor because that's a FET, but if it was bipolar, there would be the emitter resistor, and they're going, the dynamics are incredible. This is the best sound I ever heard for all of 10 minutes. If you pick a FET, though, that is, you can temperature compensate the system, of course, but if you pick a FET that simply is going through the zone where its coefficient goes from positive to negative, there's a little sweet spot there where it's right where it is. In the R100 parts out of semi-south, that's exactly right for this. It's just lucky coincidence. So in the actual production piece that I made, I elected to do without this set of adjustments. And in fact, generally speaking, if I actually have a real problem, I'll pull a part out and swap it in for another one. But if you actually test the devices themselves, you can match or unmatch them sufficiently to get this any second harmonic or not that you're looking for. And there's one more trick that works, which is you can take some small value of resistance and load it across these coils, either this one or this one, and that'll imbalance it just a little bit. The lowest value you can throw across those values, across those coils, is about 200 ohms and still works pretty good. Something more like 1,000 ohms is probably appropriate. So the alternative to having degeneration and making these adjustments here is to simply stick a value of resistor in there and trim that out. But I will say, I don't even bother at this point. The product sounds good. It sounds good with a second harmonic. And if I wish a little more positive versus negative phase harmonic, I'll just make sure that the positive transistor, for instance, has a little bit higher transconductance. That's easily tested for. So that's that circuit. It has a power supply. If I can see the next one. You've seen this power supply many times. Here it is again. This is my standard first watty kind of power supply. I've been beefing them up lately for the SITs, but this is the old one I've been using. It's got 18-volt secondaries that you can get from forgot their names. Okay, Antec is a good source for those, and you can be wired for 120 or 240. It's got a thermistor isolating the chassis ground. This is a hard chassis ground going to AC. It's got a nice thermistor that isolates that from the ground, the analog ground of the circuit, so that you have a safety connection, but at the same time doesn't tend to generate ground loops. And it's got a CRC network. You don't have to use any of this. This is just a sample circuit. You can put coils in there. You can use that not at all. With a little bit of decoupling, I'm getting noise figures on the order of about 100 microvolts or so. I consider that to be quite good. I have seen better, but I rarely achieve it in any kind of a large amplifier, certainly. There is also, this is the mono version, okay? And then on the next one, if you happen to want to divide that into a stereo piece, it's the same thing except you can split the RCs out for channel A, channel B, put a little isolation between the two channels so that they don't modulate so much on the supply. You're free to put in lots of capacitors here. Doesn't bother me at all. People ask me, how much, if I'm using values like these, and these could be half ohm or 1 ohm resistors, and the net is relatively small, but it still does a tremendous job of filtering the ripple out of the supply. It takes a real edge off of it so that the hum is not only a lot less, but it's a lot less obnoxious, has lower order harmonics. People ask, though, how much capacitance should I put here versus there? And the answer is there's no rule. I do half and half because then it looks nice, even Steven. But I will tell you that you don't want to be stingy on the first ones because the ripple currents going through them are quite high. And I've seen examples where the amplifiers, after a while, they still worked fine, but the plastic housing and heat shrink that was on the capacitor had continued to shrink till it was just a little film. And that tells me that that it was working too hard because it was taking all the ripple current. The ripple current is very high, is short duration, very high pulses, and because the energy is the size of the square of the pulse, but the duration is only an inverse of the pulse, proportionally more energy goes into that, and so you start seeing a lot of heat. That's actually one of the rationales for having thyristors in these circuits because it helps take that whole thing down a little bit. The last slide. Oh, this is the actual amplifier. Somebody wanted me to open up the one that's down the hall, and I chose not to because this was the very first version, and it really looked rather neat with all the original circuit. This was before, though, I had to make it actually work. And so if you look at the one now, it is not so nice looking. It has actually fewer parts, but they are arrayed in kind of a spider webby fashion. But there it is. That's what it looks like. And let's see. Unless I'm mistaken, that's the end of my presentation. So, any questions? Yes.
The regeneration resistors.
Degeneration.
Degeneration. The most common kind would probably be the sand-filled little block things. I think they use a nichrome wire.
Yeah, and it has a little bit of inductance to it, maybe.
Yeah, I think I've measured distortion in those before. Do you recommend or disrecommend those or any other material?
You know, I use just a metal oxide film. It's actually, I mean, you can go get very snazzy resistors, and at some point you're spending a lot of money, but you're not moving in a direction that's going to take you very far. The whole thing of eye candy parts is great. I have no objection to anybody who wants to, use gold-plated anything. And there's some really nice parts out there. And I'll be the last person to argue that they're not better. What they are is they're a lot more expensive. And I'll be honest, the one thing I can tell you about DIYers is they're really cheap guys. They go, Mr. Pass, that transformer costs $30. I can't afford that. And okay, but so I don't automatically point people toward expensive parts. I as a default, I use regular old crummy parts. And people go, why did you pick a 220 microfarad cap for that value? I go, because I have thousands and thousands of them on the shelf. So I reach over there, and until somebody finds a reason why I need to have something else, that's what I tend to use. So, and when you look at the wire on my speakers in our display, you'll see Fry's 18-gauge copper wire. It's nice, clean wire. I mean, it's not oxidized or anything. It's nice, and it's not coated with that goop that you get on some of the cheaper, really cheapo wires. But there's nothing special about it at all. It works fine. I also have some very, very nice wires that they work a little better, but I'm not here to present those. As far as I'm concerned, if you build one of these amps with the cheap parts and and it sounds good, then the design gets all the credit. And if you want to gild the lily, and take it up a notch on all of these things, that's great. I have zero argument with that, and I don't even consider it a waste of money. I personally often spend fabulous amounts of money on stupid things. And I'm usually happy with that, so it's not a problem. But, so the nichrome wire in the sandbox, I don't buy those mostly because I think they're kind of ugly.
It's like you can get PSUD for free, you can get Spice for free,
I find the easiest stuff is microcap. If you get the student edition, that's the dumbest of them all, not necessarily the most powerful, but it's extremely dumb and easy to get going with. And last time I looked, John Curl was still using it, so there we are. And I'm with you, Anything else?
Guitar amplifiers, the contrast between British and American amplifiers are almost very similar. But the tones are differentiated because the Brits have the ring start on the opposite end of the coil that flips the polarity of the speaker. It comes out, or it goes in instead of out and positive. You say that if we do a little bit more second order harmonics on the top or the bottom side, changes the character. Have you tried flipping the polarity on the speaker and see?
Absolutely. Absolutely. One of the most fascinating things, and this is, I really discovered this, the whole thing about absolute phase ties right into this. How much can you hear absolute phase? Not whether your speakers are in and out of phase with each other, but absolute phase coming through. It is becoming quite apparent, and for me, it's only recently that it's become really apparent, such that we can duplicate it regularly, that it matters a lot. But it matters a lot in the context of how you look at the second harmonic structure of the amplifier as relates to the speaker, and it matters a lot relative to what we're talking about when you're talking about what came out of the recording process. I mentioned earlier the positive going phase for a second harmonic. That one where the second harmonic wave is going positive at the same time that the main wave is going positive, and it's also going positive when the negative of the output is going positive. That's why it's a second harmonic. But the point being is that has a particular sound. If you flip that characteristic, it's got a different sound. Now, I'm not here to tell you which you like. I've noticed that I get people who like it this way or they like it that way. But I can tell you that you can pick one of those, and when you get reasonably experienced at listening to that sort of thing, you can then start going through your music collection and deciding which of these recordings were in phase and out of phase, because the effect flips. I find that totally fascinating. And it relates to something I can talk about very briefly. It's one of my favorite little soapboxes, and I won't bore you with for a moment. But if you go into the literature of psychoacoustic perception, and there's a very good book by Diana Deutsch on this subject, and in it they have chapters regarding basically how the low-level neural networks in your brain take the data from the ear and what they do with it as this little bureaucracy at the bottom, like the clerks at the DMV, and how this stuff slowly, decisions are made. And the first decisions that are made are called grouping mechanisms. What goes with what? And you've got a neural circuit that gets two pieces of information and has to decide whether they go together or they don't go together. Now, it's this real simple kind of a binary decision to be making, but of course you've got an army of these things making those decisions. And this information goes up a level, more decisions are made based on that, and there is a hierarchy. And the guy behind the screen, behind your eyes, the guy that you think of as your consciousness, is the guy who gets the executive summary. He is the guy who also doesn't decide anything. Your arm has already moved, and then he gets the information long after the muscles have been told about it. So there's this whole thing going on in your brain, but the grouping mechanisms sense amplitudes, they sense frequencies, and in sensing frequencies and amplitudes, they make decisions about which ones go with which. And harmonics being related by numerical order. They make decisions about these sounds came from that animal that's coming out of the bush after me. And again, Siegfried can speak to that just a moment. Siegfried can speak to that very eloquently. The point here is all these things are of a piece. And what are we doing when we play with distortion in an amplifier? Well, we're just fooling ourselves. We're just fooling the ear. But sometimes that's a good thing. If you tag sound in a particular characteristic, in a particular way, and I'm not saying that I know exactly how to do it, but I'm saying that I have observed it, then it slips through these systems like poop through a goose. And the decision-making process is made a lot easier. Now, yeah, it's not accurate, okay, but there it is, and people, a lot of them, like it. The other end of it, though, is there's a lot of work going on when we're talking about listening. Like I said, you've got an army of neurons working this angle, and if you make their life easier, they aren't working as hard. And when you talk about listener fatigue, when you talk about people who go, just shut it off, because after a half hour I'm tired of listening, versus guys who sit and listen to it all night and go through their entire record collection, we get both types. We get to see that. Well, one of them's tired. When they say use the word fatigue, they're not fooling around. Brain's tired. So why do we try to fool the ear? Because it makes people happy. It makes it easier to listen to stuff. And we don't really, I'm not here to deliberately create distortion, but I'm going to have distortion no matter what. I can at least organize it the way I want. Well, I guess I'm done. All right, thank you very much.